Hello. This video today is going to start us off in chapter 15, where we're going to work with integrals of multivariate functions. So in Calculus 1 and 2, we learned how to integrate a single variable function, and that required just one integral. Now we're going to be looking at double integrals and triple integrals. So a double integral will coincide with a function of two variables, and a triple integral will coincide with a function of three variables. So we start off with the two variables in our double integrals, and we're going to focus for just a moment in 15.1 over rectangular regions of integration. So I've got this great picture right here, and in this picture, I'm showing above, on top, there's this surface right here, okay, some random surface, and underneath it, projected onto the XY plane, is the region of integration, and it is a rectangle. And because it is a rectangle, it could get broken up into a bunch of itty-bitty slices. These are dy's that I'm slicing on here. And then similarly, we could break up our x into itty-bitty slices. So those are going to be dx's that I'm slicing up. And then when we put those all together, we have a whole bunch of little itty-bitty rectangles, and each one of those has an area, okay? To calculate these values, well, we have an initial x value of a and a final x value of b, so b minus a divided by the number of rectangles we wish to have. That's going to give us the length of our delta x, and similarly for delta y, if we have c as the initial y value and d is the final y value, and we want to cut our strips into n rectangles, then we would take d minus c and divide it by n. That would give us the length of each of the delta y's. Now this is for the case of approximating what we're calculating. What I want to go over really here is like, what are we calculating when we work with a double integral? So I'm going to go in here and erase those lines there, and I want to focus on just, looking at one of these little rectangles. If I was to draw a column up to the surface, then here's what I've got. This is like a column, and it's three-dimensional, and it has a volume. So the idea here is that we're going to break up the region R on the XY plane into like an infinite number of little tiny rectangles, and then we're going to imagine a column coming out from the XY plane up to the surface, and the surface is going to act like a roof. We're going to calculate all the volumes of those itty-bitty columns, and we'll take those volumes and add them together. And that's going to give us the overall volume under the surface and above the XY plane. So that's kind of what all of this is saying in here. Now we could work with the midpoint rule and the right-hand rule and the left-hand rule don't really apply too well here, because we have upper left, upper right, lower left, and lower right, but we could look at a midpoint. My focus in our class is actually not on the approximation methods. I think that you should know about them, and that's what's happening when we look at a double integral, is that we're adding up an infinite number of volumes of little itty-bitty columns that come up from these delta x, delta y rectangles. Okay, so this picture right here is just showing you the XY plane broken up into these itty-bitty rectangles, and then the idea that we could pick, any point in each of these rectangles that would give us the best value of the volume, and then we could sum up those values. So just looking at this f of x sub ij, y sub ij, those are z values. And the z values give the value of the height of the column. And then the delta A, that's going to be delta x times delta y, which is going to be the area. So if we have an area of the base times the height of the column, that's going to give us a volume. And we're going to have an infinite number of those, and we're going to add them all up. And then we're going to take a limit on that. Like basically the limit is being taken on the number of rectangles that we create. We want there to be an infinite number of those. So if we take the limit on that double sum, we're going to get a double integral. And that is what we're going to focus on. Now, we're going to focus first in 15.1 on a situation where we are actually just integrating over a rectangle. Now, a rectangle, because of its shape, the bounds on a rectangle are from a number to a number, right? They're not going to be a function to a function. And so we can pick our numbers to be a and b for x and c and d for y. Now, let's see, where do I want to go? Okay, let's go right here to this one. This first representation, on the left-hand side, I'm showing an order of dy dx. And the integrals, I'm showing an integral from a to b and an integral from c to d. What we have to know is which one goes with which. And the rule is to work from the inside out. Okay, so we're going to start with the innermost integral. And here I've got some brackets to really stress this. We've got brackets around the innermost integral symbol and the innermost differential. So that means the integral from c to d goes with dy, okay? And when we integrate f of xy with respect to y, we're not going to like completely ignore x, but we're going to treat x like a constant. You know, pick your favorite number, 13 or 7 or whatever. We're going to treat x like that, and then we're going to integrate, okay? Once we have integrated with respect to y, we're going to evaluate it from c to d, and then we're going to have a function left. It'll still have x's in it. And then we're going to integrate the outside. And so the outside will be the integral from a to b, and that will be with respect to dx. Okay, so we'll integrate with respect to x. We shouldn't have any y's in there now because we already took care of y. We're integrating with respect to x. We'll get a function of x. We evaluate it from a to b, and we're going to get a number. So we should never get a function when we're done. It should be a number, okay? Might be an ugly number, but it's still a number. Now this next representation, things are in a different order, okay? And this is to really signify that we can switch the order when we are integrating. So in this one, the integrals now are in the opposite order. First I have the integral from c to d, then I have the integral from a to b. But notice, the differentials switch too. Instead of dy dx, I now have dx dy. So I'm examining this and, you know, it's like which one goes with which. Let's go to our golden rule. The innermost integral will go with the innermost differential. So the integral from a to b goes with dx, whereas the integral from c to d can only go with dy. So again, we're going to integrate f of xy with respect to x, which means we will treat y like a constant, okay? It's very similar to what we were doing before when we're differentiating a multivariate function. If we're finding a derivative with respect to x, then y is a constant. If we're finding a derivative with respect to y, then x is a constant. So those rules are still going to be playing a part in here. And again, the overall result will be a number. Can't stress that enough. If you're getting x's and y's left after you've integrated, something went wrong, okay? All right, so the cool thing about, you know, integrating over an integral is that it doesn't matter which way we integrate, and that's what I'm trying to show you in these two expressions up here. The only thing that matters is that the right numbers are going with the right differential. So the bounds for x go with dx. The bounds for y go with dy. Don't mix that up. Okay, if you switch the order of your integrals, you need to switch the order of your differentials. All right. And so here's our final statement on, this is Fubini's theorem. Fubini's a mathematician who proved that this was true, that when we're integrating over rectangular regions, it doesn't matter the order. I need you to keep in mind, this is only true for rectangular regions. Okay, so after 15.1, this isn't true. Okay, we're going to have to work with things differently. One of the cool little theorems that we'll get out of here is if we want to find the average value of a function f, and if we think of f as like a surface and it's a height, then if we're finding the average value of the function in two variables, we're finding the average height of something. I always like to think of my surfaces as like a fancy roof for a building. And if it's a fancy roof, then it's going to have curves. It's not going to be the same flat roofs that we see in Arizona. There's going to be curves. It's going to have high points and low points and whatnot. And maybe we want to find the average value of the height of that roof. Well, we have a formula right here, and it says F average. What we're going to do is we're going to divide out the area of the region of integration after we integrate over the region of integration, the f of xy. Okay? All right, so let's get started working with some examples. In this first one, the integral, it's a double integral over r. R is our region. The integrand is 5 minus x, and our differential is dA. And we're told where r equals, and this is some funky notation right here, r equals an interval 0 to 5 crossed with an interval 0 to 3. We need to know what that means, okay? The first one is always x values. The second one is always y values. So what you're being given when you're given this notation is the lower bound for x and the upper bound for x, and then the lower bound for y and the upper bound for y. And we're told that this integral represents the volume of a solid, and we're actually just being asked to sketch the solid here. Okay, so that's fun. We'll sketch it, and we'll also set up an integral and solve it, because why not? So I want to graph this, and let's see, z is equal to 5 minus x. If I was to move the x over, this is x plus z is equal to 5. That's a plane, and that plane is parallel to the y-axis since y is not involved in my equation. So I'm going to draw this. And the way I draw planes is I just draw the intercepts, because that's the easiest way for me to do it. 2, 3, 4, 5. So if x is 0, then z will be 5. That's an intercept. If z is 0, then x will be 5. There's another intercept. I can connect these two dots to give me a line, and then I'm going to draw these over parallel to the y-axis so I can see my plane. Okay, that's my plane in space. Now, the region of integration, it's telling me that it is, and I'm going to use a different color here, my region of integration, my x values go from 0 to 5. Okay, I've already got that. And that's going to be, my y values go from 0 to 3. Okay, so now I can draw parallel lines to indicate the other sides of that rectangle. Okay, this is my region of integration. Okay, and I want to find what is going to amount to being the amount of volume that is underneath this slanted plane and above the xy plane. Okay, so my solid, I've got to get that in there. I don't quite have my solid in yet. My solid over the region of integration. Okay, I've got that. And I have that. Now it looks like I can erase some of my plane here so that we can just focus on the solid. Okay, it looks like a solid triangular shape that we have here. I can think of a wooden block that my son has. It looks just like one of those wooden blocks. All right, so that's all we were asked to do, sketch the solid, but I want to go ahead and work through the integral. So this integral, the integral, double integral over r of 5 minus x dA, I need to get my bounds in there and I need to get my differentials in there. So I'm going to use Fubini's theorem, which tells me it doesn't matter what order I go in. So I'm going to go ahead and put my bounds for x in second. I'll put my bounds for y in first. The bounds for y are 0 to 3. The bounds for x are 0 to 5. My integrand is 5 minus x. And because 0 to 5 is the innermost integral, and those are x values, that means dx needs to be my innermost differential, and dy will be on the outside. Then I can draw something in here that just helps me to focus my eyes on what I'm doing first, okay? So it looks like I'm integrating with respect to x first. And that means that when I write my equal sign, I do not get rid of my integral from 0 to 3. It is still there, okay? But inside now, I'm going to go ahead and find the antiderivative of 5 minus x with respect to x. It will be 5x minus 1/2 x squared. And I'm going to evaluate that from 0 to 5. After I evaluate that, then I'll be able to integrate with respect to y. So I have my dy on the outside on the right, and I have my integral on the left on the outside. So inside, I'm going to have a new integrand, but I need to evaluate to figure out what it is. So I'm going to go ahead and figure that out. It's my integral from 0 to 3. I'm going to evaluate at 5. I have 5 times 5 minus 1/2 times 5 squared minus 5 times 0 minus 1/2 times 0 squared. Close all that. Still have my dy. Okay, obviously the contribution from x equals 0 is a whole lot of nothing. But when I simplify this, it looks like my integrand now is, so I'm going 0 to 3, 25 minus 25 halves dy. 25 minus 25 halves is going to be 25 halves. So I have 0 to 3, 25 halves dy. And if I integrate this with respect to y, I'm integrating a constant, so I'll just get the constant times y, and that'll be evaluated from 0 to 3. So this is equal to 25 halves times 3 minus 0, or in other words, 75 over 2. Okay, that's it. That's what we got. So the value of the volume, so this is the volume of the solid, and it is 75 over 2 cubic units, whatever they happen to be. Okay, next question, we're supposed to calculate a double integral, and now they're not asking us to sketch anything. That's fine. We're given a rectangular region. Remember the first interval, that's going to be x values, and the second interval, those are going to be y values. And it doesn't really matter which order I go in. I have Fubini's theorem saying just do what you like. So I'm going to write this as the integral, and I'm going to switch it up. My outer integral will now be my x values from 1 to 2. My inner integral will now be y values from 0 to 1. My integrand is x plus e to the minus y. Now, because the inner integral is y values, that means the inner differential is dy, and the outer differential is dx. Again, I'm going to put those brackets in so I can focus my eyes on what I need to do first. All right, so I'm integrating with respect to y. And there's that term x. Remember, x is a constant, and the antiderivative of a constant is just the constant times the variable. So when I find this antiderivative, I still have the integral from 1 to 2. Now my antiderivative is xy for that first term. The antiderivative of e to the minus y is minus e to the minus y. This will all get evaluated from 0 to 1. Close that up, and then dx will be on the outside. So the 0 to 1, we need to pay close attention and realize those are y values. Don't you dare touch the x. It's a variable. It's going to stay a variable. until we integrate it. So I'm going to plug in my 1 and my 0. My integral still goes from 1 to 2. Evaluating at 1, I get x times 1 minus e to the minus 1 minus, in parentheses, x times 0 minus e to the 0. All right, and when this simplifies, I've got an x times 0. That's just going to go to 0. E to the 0 is 1, right? Okay, let's put this together. This is going to give me the integral from 1 to 2 of x minus e to the minus 1 plus 1 dx. Okay, now I keep going. If I find the antiderivative with respect to x, I'm going to get 1/2 x squared minus e to the minus 1 times x plus x, all getting evaluated from 1 to 2. Okay, plugging those in the evaluation, I have 1/2 times 2 squared minus 2e to the minus 1 plus 2 minus, in parentheses, 1/2 times 1 squared minus e to the minus 1 plus 1. Combining all my like terms, it looks like I have 4/2 and 1/2, which gives me 3/2. I have a minus 2 e to the minus 1, and I have a plus e to the minus 1, so it's going to be minus just one of those e to the minus 1s. And I have a 2 minus 1, which leaves me with a plus 1. I can simplify this just a little bit more. It gives me 5/2 minus e to the minus 1. Don't you dare approximate that. That is an exact answer. Okay, so we'll leave it as it is. No calculators needed. Okay, so that's how we would work through a couple of problems where they give us the region and we just need to figure out where our bounds go, how to set everything up. In this next example, we're calculating another double integral, but they have already gone ahead and put the bounds in. All we have to do is get our focus. So I'm going to put some brackets around the innermost integral and the innermost differential so that I can see very clearly that I am integrating with respect to x first. Now, what may be helpful for some of you is to maybe rewrite the integrand so that you can see things a little bit more clearly. This is equal to the integral from minus 3 to 3 of the integral from 0 to 1 of, and now I'm going to factor that y squared out and leave behind an x over x squared plus 1. And then there's my dx, my bracket, and my dy. The reason I did that is because y squared is a constant. We are integrating with respect to x. So anything that's a y is a constant. And so and this is a constant multiplier. It's like a 7, right? So I can just pull it out in front and kind of ignore it. I'm not getting rid of it. I'm just ignoring it for a moment so I can focus my eyes on integrating x over x squared plus 1. This is a u sub. Okay, so I'm going to go over here and do my u sub. I should let u be the denominator, x squared plus 1. Then du is 2x dx, so 1/2 du will replace x dx. And then I'm going to go down here and I'm going to work with the indefinite integral in terms of u. So it looks like I have a 1/2 times the integral of 1 over u du, which is just 1/2 ln of the absolute value of u. Okay, now I can go back to my problem and rewrite this, the integral from minus 3 to 3 of, I still have a y squared, but then I also have times a 1/2 ln of the absolute value of x squared plus 1. And this is all getting evaluated from 0 to 1. And then once we do that evaluation, we'll be able to integrate with respect to y. All right, so evaluating, I'm going to plug in 1 and then 0. So the integral from minus 3 to 3 of, plugging, remember y squared is just going to hang out. So I'm going to pull it out and focus on my evaluation. I have 1/2 ln of 2 minus 1/2 ln of 1, and then a dy. I think I have extra brackets here. Ln of 1 is 0, so that second term is gone. Okay, so then we can focus on just, well, it looks like the 1/2 ln of 2 is just a constant. So I have 1/2 ln of 2 times the integral from -3 to 3 of y squared dy. So just kind of getting rid of anything that's extra, evaluating anything that's easily evaluated and gotten rid of. And then I factored my constant out so I could focus on that y squared. The antiderivative of y squared is 1/3 y cubed. And so that 1/3 can come out and join the 1/2. I get a 1/6 ln of 2 y cubed from -3 to 3. That gives me 1/6 ln of 2 times 3 cubed minus a -3 cubed. 3 cubed is 27, and -3 cubed is -27. So this gives me 1/6 ln of 2 times 27 minus a -27. So that's going to give me a total of 54. I have 54 over 6 ln of 2. And 6 goes into 54 9 times. Finally, we have 9 times ln of 2. That's our final answer. Okay, so this one required a bit more work. We had a u substitution involved in this whole multivariate thing. That's going to happen. And so you're going to have to practice how to handle like the extra variables that are hanging out, right? Just got to treat them like constants. Let's try another one. In here, we need to find the volume of the solid that is enclosed by the surface z equals 1 plus x squared y e to the y. And then by the planes, z equals 0, x equals plus or minus 1, y equals 0, and y equals 1. So the z equals 0, that's just the xy plane. Okay, that's my lower bound. But if we were to like really think about what how you calculate volume, we would have a double integral over our region, and we would have the top, like the highest z value, minus the bottom, right? So height, you take the biggest value, you subtract the smallest value, and then you have the overall height, and then you would integrate that with respect to dA. So when we're given something like, oh, okay, it's bounded by this surface z equals, and I get some function, and then z equals 0, that's kind of telling me some pieces I can put into my integrand. So that's saying I have an integral, double integral over r of 1 plus x squared y e to the y minus 0, because the floor, the bottom, is 0. Now, obviously, we don't write the minus 0, but it is good to get in, like, to tie together a double integral with this idea of taking a top function and subtracting a bottom function. It will go far in helping us later on. Okay. Now I need to figure out my bounds, and I'm looking at the x values that are given. These guys right here, these are defining my r. And so I can see right away x is going from -1 to 1, and y is going from 0 to 1. So when I rewrite my integral now, I can decide what I want to do first. I'm thinking I want to do my x's, like that's what I want to integrate first. So I'm going to put my y bounds on the outside, 0 to 1, my x bounds on the inside, -1 to 1. I have my integrand, 1 plus x squared y e to the y. Since x is the x integral is the innermost one, that means dx is the innermost differential, and then dy. And then I'll put some brackets in here just to train my eyes. All right, integrating with respect to x, remember all the y's are just constants. That's it. So this gives me the integral from 0 to 1 Excuse me, had to sneeze. All right, and then the integral with respect to x. The antiderivative of 1 will be x. The antiderivative of the x squared y e to the y e to the y is just going to stay there. It's a multiplier. The x squared is where we focus. That gives us a 1/3 x cubed y e to the y. And we're going from -1 to 1. And then we'll have our dy after we evaluate that. So plugging in 1 and then subtracting the evaluation at -1. Remember, we are plugging in for x. Y is going to come later. So this is the integral from 0 to 1 of, plugging in 1, I get 1 plus 1/3 times 1 cubed y e to the y, minus in parentheses a -1 plus 1/3 times -1 cubed y e to the y. And then I have my dy on the outside. So I always write everything out because, as we've seen in class, arithmetic is really, really hard. And it's so easy to make mistakes, especially if you don't see them. So I'm going to write this out again. The integral from 0 to 1 of 1 plus 1/3 y e to the y. Distributing the negative, I get plus 1. In the second term, that -1 cubed gives me a minus sign. But then I'm distributing another minus sign through, so it'll be plus 1/3 y e to the y. And then I can combine like terms, and finally I get the integral from 0 to 1 of 2 plus 2/3 y e to the y dy. All right, that's not bad. Looks like we have an integration by parts though. So this y e to the y, we have to deal with the integration by parts. So I'll do that over here on the side. When we have a polynomial and an exponential, the u is always the polynomial. So u is equal to y, and du is equal to 1 dy. Dv is going to be the exponential, e to the y dy, and then v will be e to the y. So in my uv minus the integral of v du, I get y e to the y minus the integral of e to the y dy, which finally gives us y e to the y minus e to the y. Okay, next line. All right, I'm going to integrate everything and put in what I got from my integration by parts. The antiderivative of 2 with respect to y gives me 2y, and then I have plus 2/3, and the antiderivative of y e to the y is y e to the y minus e to the y. We're evaluating all of this from 0 to 1. All right, plugging in 1 and then subtracting the evaluation at 0, we get 2 plus 2/3 times e minus e minus, in parentheses, 0 plus 2/3 times 0 minus e to the 0. Okay. The e minus e, well, that's going away. That gives us 0 right there. So I have 2, and then I have, it looks like minus 2/3 times a minus 1, because e to the 0 is 1. So it's 2 plus 2/3. I'm going to rewrite my 2 as 6/3. So I have 6/3 plus 2/3, which gives me a grand total of 8/3. Now, of course, in your final calculation, you can use a calculator to add any fractions and whatnot. If they're simple enough, I'll do them in my head, but other than that, I use my calculator because, again, arithmetic is hard. So that's the conclusion of 15.1, where we're working with a rectangular region. In the next section, we're going to make our region of integration more difficult, and we'll see what sorts of things we need to do in order to work with more general regions. In the meantime, if there are any questions on 15.1, please reach out.